try to present a methodology that we are applying in order to observe in the same picture together the ship and the human element, because the challenge of designers is to have exactly a framework where we can make our design considerations and where we can carry out our decision-making process during the design of the ship. The trend is that in order to enhance ship efficiency, we are taking advantage more and more about control and monitoring, about automation on board. And please be aware that I spoke about enhancement of efficiency. So here there is a list of possible systems and plants on board that can be under automation. And here there is a list of possible parameters that are measured by automation, and they are in the context of control of the ship. The point is that automation, it's likely to fix things that are based on rule performances and skill performances by crew members. So easy tasks are likely to be easier. The point is that it remains on the shoulders of crew members the most difficult part of the job. So if we are going to take on board clumsy automation, maybe we can get that easy tasks are easier, but hard tasks are likely to be even harder. And this is a safety issue. So we are starting from efficiency, but then at the end we find that we might have a safety issue. So here there is the place where we need to find out a design process that can help to discuss about integrated human and automation system. We have mentioned this morning that it might be smart to give a look to other transport mode, what others are doing on this topic. And we selected, after this overview, the STAMP methodology, that is a system theoretic accident model process that is very good in helping an interdisciplinary, let's say, approach. And it is also able to take into account social organizational aspects. As you can see, let's say the origin of STAMP methodology is from MIT, and the professor that started to develop and to use this methodology is Professor Nancy Leveson and her research team. Just a few words about STAMP. So it is a model that can help you in understanding how things could happen. So it is a causality model. It is based on system thinking, system theory, and control theory concepts. And as I told you, it is suitable for introducing also socio-technical organizational topics into the complex system. Here in this picture, you can see in general how the methodology works. First of all, the methodology is able to model elements and relations between and among elements. If you have an emergent property like safety, you can obtain that, for example, let's speak about ship safety. We can assume that the ship safety is an emergent property that can be obtained with a proper control system where we have the several items contributing to the ship safety that are also considered in terms of control actions and feedback. So in other words, accidents are the results from inadequate enforcement of the behavioral safety constraints on the process. This is what it is at the base of the STAMP methodology. Actually, the STEM methodology is based on two different approaches. One is STPA, that is the one that we are going to discuss today, and the other one is CAST. CAST is most useful for analyzing incidents, accidents when they have already happened, so it is in some way reactive. STPA is developed in order to be proactive and to help people to design safety into system, and in our case to design safety on board the ship. There is a handbook available on the website because Nancy is very supportive in developing documents in order to apply the STPA tool and also the CAST tool. From the handbook you can see that the STPA is made of 4 steps. The first one is just to define which is the system you are interested in. So you can define the system boundaries, and it means that you are able to define also the environment. And the very first part is to identify hazards and losses. It's very important to understand that as engineers, as designers, we can have a control about hazards. We cannot have a control about losses. And then I'm going to explain to you which is the difference between the two terms. We are going to analyze all the 4 steps by an application case that we are going to develop now. So the other steps are to model the control structures, then to identify the unsafe control actions, and then to identify the loss scenarios. The kind of application case that we would like to develop is a dead ship condition. Dead ship condition for on board large cruise ships. Dead ship condition means that the ship is without energy, and in our case we are focused on the hazard that the ship is without propulsion. Just to stress the difference of a typical view of the problem and what we are going to discuss today, here you can see a typical layout of an energy system on board a big cruise ship. I take the chance of this slide to comment with you that we do need automation to control such a complex system. So what I want to say is that automation is very useful, but we need to know very well what we are doing during the design process with it. So this is a very complex energy system on board the cruise ships. Automation is very useful. You see that there are the diesel generators here. They produce power that is delivered to the hotel services and to the propulsion system. As I told you before, it's very important to understand which is the difference between hazard and loss, because as technicians we can only work on hazards. And for example, the hazards that we are considering is the ship without propulsion and the ship without hotel services. But for the purpose of this paper, we focus on the ship without propulsion. In case, for example, we are in very heavy environmental conditions, air and or close to the shore, this kind of hazard is likely to become a loss. So the ship can go on the coast, and of course in that case we run the risk to lose the ship and to lose the human life. So the hazard we are focusing on in this paper is the ship is without propulsion. And now we are going to develop what it is called the safety control structure. The very basic model of a safety control structure is the definition of a controlled process. Then there is a controller that is characterized by a control algorithm and a process model, and you have the interaction, so you see control actions and feedback. In this specific paper we want to discuss also about human element, and this is the case. So we have the propulsion system, the energy system. This is automation, and this is the human being as a high-level controllers. And in this, with the stamp, with STPA, you are able to implement the interaction between the automation and the human being, because in principle, you can model everything with this general structure. This is the kind of development that Nancy makes in his book. You see that here there is the automation, here there is the control process, for example, the energy system, the propulsion system on board. This is automation, and this is the human controller. So this is the selection of a control action that can be put in force by the human controller. Both has the model of the controlled process. In this case, it is more appropriate to call it a mental model. And the mental model can be updated in this case by information from automation, because the human controller has also the model of automation. This is just the starting point that you can find on the book, because then we elaborated on this. Okay, so this is our safety control structure, the very big one, because you see that in order to point out with you that it is true that it is possible to put in evidence also socio-organizational issues. In principle, here we have the ship, the master, and then the operation management within the company, the flag state, the classification society, the IMO. It is possible to discuss a safety problem at very high level. But we are going to focus for our paper just in this frame. So we are going to take into account the human controller, the automation, the diesel generator, and then, of course, the distribution system for the propulsion, and then for the hotels. In this case, when you selected the part of the safety control structure you want to focus on, you are also requested to define the controls that are carried out by the controller on the lower level. So we wrote this list of possible controls and feedback. And then we decided to focus on a specific unsafe control action that has been selected in a very long list, because after you have defined the safety control structure, then you are ready to define the so-called unsafe control actions. The structure to define this unsafe control action is very well defined in the handbook. You have to follow this, let's say, table. There is the control action A, and then possible control actions that are not providing wrong timing order or duration too short and too long. And every time you need to write something like controller does not provide this control action when this is the context, and in this case you have also to say which is the hazard that is going to come out from this unsafe control action. So the unsafe control action is a control action that in a particular context and worst state environment will lead to an hazard, and it is every time is made with this structure. And this is the reason why it is very automatic, the generation of this unsafe control action. We got more than 100 unsafe control actions just framed in that part of the safety control structure we defined. And we selected, among this unsafe control action, we selected the one that you can read upstairs. Automation provides turn off of the requested gensets during navigation in heavy weather conditions close to another vessel, and there are not any other gensets to turn on in the sequence. And then, of course, we are going to lose propulsion, and we are going to lose generation for the hotel services. It means that the ship is at dead ship condition, and this is due to the fact that automation decided to shut down the diesel generators. The use that you make from STPA is the outcomes that you can get from STPA are this list. Let's say that maybe we are interested in this context to identify design recommendations and to identify mitigation and safeguards that are needed. So it is the final aim that we have. Whatever you are willing to obtain as an outcome from STPA, you need now to define the loss scenario. So you need to understand why the unsafe control action has happened, why the automation system has shut down the diesel generator in such a difficult situation. And in the handbook you find again a very clear roadmap. You are supposed to ask yourself two questions. The first is, why would unsafe control action occur? And then, why would control action be improperly executed or not executed? And the two questions make reference to different parts of the safety control structure. So when you want to understand why unsafe control action occur, you are much focusing on the controller and the feedback that the controllers receive. And when you are asking why the control action being properly executed or not executed, you are focusing more on the actuators or on the object of control. In our case, we decided to focus on unsafe controller behavior. So the automation made the shutdown, why the automation behaved in such a way. In turn, when you focus on the unsafe controller behavior, there are four other different options that you are assumed to consider. So the unsafe controller behavior can be in relation with failures involving the controller. So maybe the automation has a failure. Maybe the automation has an inadequate control algorithm. What we selected is that the automation received an unsafe control input from another controller because we want to speak about human elements. And then inadequate process model. You see that now it's time to understand why another controller might have delivered an unsafe control input. And in that case, we selected a publication that we found on the web, and we could observe that inside the human operator, we can select the control action selection frame, the mental model that is made in turn of other three parts, and then the mental model updates that come from the automation. In order to understand which of this part can be interested in our problem, we can focus on some suggested questions that we found in this publication. For example, dealing with the number one, control action selection. That means, how did the operator choose which control action to perform? We can ask, does the operator have multiple or conflicting goals? Or we can ask, was the operator in a complex or novel situation that required knowledge-based selection? Then, for example, about mental model, that means, what does the operator know or believe about the system? Again, we have specific questions that we can answer in order to understand which is the scenario that generated this problem. And finally, also the mental model updates. That is, how did the operator came to have their current knowledge or belief. Selecting some questions, we arrived to the definition of this scenario. The scenario that we want to discuss is that the human controller decided that it was not necessary to apply a control action in response to an automation alarm. So, for example, the automation gave an alarm of low oil pressure, but several times, but the human controllers didn't take any countermeasure, even though that kind of alarm is important for the engine safeguard. Why this could happen? probably for an inadequate mental model, so in turn an underestimation of the alarm importance, or the fact that the human controller didn't think that it was reliable, the kind of alarm that was given by the automation. So for example, speaking about number one, the decision can be a consequence of a prioritization of urgent actions regarding other several tasks, or maybe previous experience can suggest that the alarm generated by the automation is of lower priority, but we must remind that maybe the environmental conditions are very heavy, so in that case maybe it is not of such a lower priority. With regard to the second point, the non-reliance, it is possible that the operator assumes that large roll motions are having an influence on automation sensors, and that in that case the alarm is not a real alarm. In order to be practical and pragmatic, we tried to get some design suggestion from this scenario, and from let's say the capability of the automation to shut down the diesel generator close to the shore in heavy weather condition. Maybe it is better in specific cases like engine shutdown that the operators is consulted by automation system for the final executive authorization. So it is not just a matter of alarms, but in case the automation is on the point to shut down the engine, just to let the human being be aware of it. So the automation should speak more with the human controller. In particular then, it is important that also the training and education of human controller is different, and it is more and more attentive to this interaction with the automation. And the very last point that we could get from our analysis is that also the technical specification of sensors of automation can be better described, and in particular sensors should result able to function properly also, for example, in this case with heavy weather condition. So just to conclude with you, we think that STPA can be helpful in supporting us designers to discuss together about the ship as a technical product and together with human beings, especially in the design phase. This is going to be very important the more we are going to rely on automation, and I think that this is going to be a very hot topic, as you know, in the 21st century. It is also something that can give us suggestions where to focus in terms of training and education of seafarers, and it is also very useful in order to put in practice what we define now design for operations. So design for operation is a very nice topic, but we need tool and methodologies as we discussed this morning, and STPA might be a good methodology. Thank you.